Welcome to a lesson with Dr. Powell. As promised, we're going to work through the computational details of how to see that we have a local maximum or minimum of this surface at that point. Okay, so we have the first derivative, at least the parts of the first derivative. Now let's take the second derivative. So the second derivative is done in a very similar way. Just like for the first derivative, we have a matrix where we have fx, fy. We're going to do the same thing. We're going to have the first derivative here and the first derivative here, where we take x, y. The first derivative has two outputs, fx, fy, and fx, fy. So we're just going to basically do that. So basically, just think of this as a column, take derivatives with respect to x, derivatives with respect to y, and let's do that. Okay, so we take the derivative of both with respect to x first and put that in the first column. With respect to x is just 10, and the next one is just -6. Then we do it with respect to y. This with respect to y, -6. This with respect to y is 10. So this is our second derivative, and it's constant. This is a quadratic in two variables, and we get a constant second derivative. So in particular, the second derivative at this point is just this, which is nice. Okay. Now, next, we want to see if we can find two scalars that this matrix will behave like in certain directions for certain runs. So let's just kind of, for example, put something in like this, and suppose for this particular vector, this matrix is behaving like a scalar. Let's suppose it behaves like a scalar. I'm just going to use x as the scalar. I mean, it's not going to be related to that x. It's just going to be x, and you'll see why I'm using that in a minute. But that means that it's going to behave like this. It's going to behave like a multiplication by a scalar x, like this. You just multiply u1 by x. This is in the x component, and that in the y component by that. Okay, awesome. So this is what we would like to have happen. Now, let's look at another instance where this might happen. Let's come up with a simple matrix that would actually guarantee such a fact. What if we were just to use x0? Think of the dot product of x0 and that. Don't you get xu1? And what about 0x? Once you get that dotted with that, once you get xu2? And you do, which means that means that these are behaving the same on this. So in particular, if we were to subtract the two, then two matrices, so we take this matrix, subtract that matrix, we get a new matrix which are behaving like 0 in that direction. That means something about that matrix. That means that, in particular, that if you look at this matrix and think about after you subtract, and you think about the rows or the columns, and you think about a cross product and areas or whatnot, it'll actually be 0, or the determinant, you could say, is 0. And that condition is going to give us what the scalars should be. Let's take a look at that. But I'm going to reverse this a little bit just for ease of computation. I'm going to put the minus on this guy, and I'm going to put the plus on this guy. Okay. So this is going to look like, so let's distribute that negative in though. So, okay. So when we make this computation, we should get a matrix that has determinant 0. So going through that, just adding them now, we have x minus 10, 6, 6, and x minus 10. Just adding what I have after I distribute the negative. So this is just going to behave like the 0 matrix in a direction or two, a couple different at least one direction, which means its determinant in particular will be 0. Take the determinant of this. Let's see what we get. So what does that mean? That means to do a lot like we do for the cross product. You just do this minus that. So we get x minus 10 quantity squared minus 36. Work that out. We have x squared minus 20x plus 100 minus 36. This right here is 64. And then this actually factors as x minus 16 and x minus 4. So if this were equal to 0, we want the determinant to be 0. That's what we're aiming for here. We've actually found the scalars. And there actually are vectors that, if you can find these scalars in this computation, actually there's a way of relating the x and thinking of it simultaneously as a scalar and a matrix, and even looking at the columns of that matrix and kind of playing with it a little bit. If you're able to get to this point, you've actually also in some way computationally shown that you actually have vectors and directions that actually where the matrix behaves like the scalars that are solutions to this. In other words, like the scalar plus 16 or the scalar plus 4. Notice how both of these scalars are positive. That means that as we move away, that means that the gradient is going to be in line with the directions that are heading out. Because this is positive, so it's a positive multiple of thing. The derivative it changes positively according to the direction where I'm heading. And so a positive dot product, so it's perfect for a minimum. So if you get to this point, you find positive roots right here, then you know for sure you have a minimum. There are formulas that are given in other places in books and so forth for that actually are in conditions that actually guarantee that these roots are positive. And you're free to look at those, and I'll even mention them as well at some point. But the reason why I'm going over this way is because it's nice and intuitive and pleasing to the mind, at least in thinking about it. But also it's applicable so much more than what they give in the book or in other places. Use this exact same idea no matter how many input variables you have. And you still have a very solid idea whether you have a minimum or maximum if you're optimizing situation. So you actually have a lot more applicability here if you look at this. And besides, you can use a computer to make this computation very quickly and to even see that the roots are all positive or negative. Thanks for watching.